And then also some qualitative things about forces. Like I give you a collection of charges and I just ask you, what is the direction of the force? Where you're not calculating something, you're just sketching out the vectors and then adding them up in your mind and then showing me the direction of the force. Or vice versa, I could give you a collection of charges and ask you, or show you the force and ask you what are the signs of the charges. All right. That's forces. With fields, you'll see a simple kinematics problem like we had in the homework. I have a charge in an electric field. What is its velocity? What is its position after so much time? Just calculating the magnitude of an electric field or the direction also could be in 2 dimensions. A couple of things about electric field lines. Interpreting electric field lines, the direction of the lines gives the direction of the electric field, the density of the lines gives the magnitude of the field, and then we get into potential, calculating the potential due to a collection of point charges, talking about the work that's required to move a charge through a potential. We had some questions like that in the concept test. Calculating the potential energy contained in a collection of charges. And I think that's all the topics. That is all the topics. All right? All those are somewhat familiar to you, I hope, those various topics. The 4 quizzes sort of track out the 4 different big groups. So I'm just going to start looking at the exams. And we'll go through and work through some of the problems. Is that an okay tack for you? Again, if you have questions along the way, we can certainly just take a break and we'll step back and we'll look at those. Oh, all right. Make this bigger. How to get rid of this thing? Oh, that doesn't matter. Let's see. What particular topics would you like to go over first? Potential. All right, let's look at that. That's probably the most difficult of them all. All right, so when you're talking about potential, one problem that you'll have is just you have a collection of charges and you want to find the potential at a particular point. So for example, I have these charges here and I want to find the potential at that point A. Remember, potential adds as a scalar quantity, so you just add them up. And so I just say V equals KQ over R plus KQ over R. This is Q1, R1, Q2, R2. By the way, I'm looking at last year's exam. This is spring 14. And then all the exams that you should be looking at should just be exam 1s. Most of your exam 1s, by the way, are going to be similar in topics. Sometimes you might run into capacitors on some of these exam 1s, but not usually. All right, so I have 9 times 10 to the 9th. Q here for Q1, we'll call this Q1 and this Q2. Q1 is 9 times 10 to the minus 9. Remember that nano is minus 9 divided by 3. Plus 9 times 10 to the 9th. Q2 is 4, but it's negative 4 times 10 to the minus 9 divided by 2. So that's KQ over R. Listen, guys, on the test, it'll really help you a lot if you know how to get rid of these various exponents, because I like to give you numbers that give you nice round answers. So if, like for example here, I can cancel out that 10 to the 9th and 10 to the minus 9. I can also cancel out this 3 with a 3 in that 9. And so the first part of this is just 27. Right? So it really helps you, because you often make mistakes. I know I make mistakes. When I start putting numbers in calculators, I hit a button wrong or whatever, because I got big old fat fingers and I hit the buttons wrong. So anyway, it just helps you if you know how to do that type of simplification. Over here, the 10 to the 9th, 10 to the minus 9 go away, and this 2 cancels out with one of these 2, and I'm left with negative 18, and so that's 9 volts. So the answer is 9 volts. you'll certainly have a problem like that where you have to calculate the potential due to a collection of charges. It'll be 2 charges, maybe 3 charges, but definitely not more than 3 charges. All right, I think y'all are probably okay with that, right? Yeah, so we practice it. You'll definitely have a problem like that. You'll have a problem like this one too, where I have a collection of charges like this, and I want to know where along the line is the potential equal to 0. All right, so on these, since V is equal to KQ over R, I want to find the point where positive and negative charges are the same distance from that point. So let me pick one that's not the answer. So for example, at point C, I have a distance from the -1 and the +1 Coulomb charge. Those aren't the same, so the potentials don't cancel out. All right. The potential due to the negative charge is bigger than the potential due to the positive charge, so they don't cancel one another out. All right. Similarly, these don't cancel out because they're different distances. Now, these 2 charges, their potentials do cancel out. So those 2 charges contribute a net potential of 0, but the others do not. All right. Let's see. So that's not. So C was not the right answer because the potential is not 0. The right answer is, what is it? It's B, right. So right here, it's B because I have a distance from there to there, so the potential equals 0. From here to here is the same as from here to here, so the potential equals 0. And then from here to here is the same, so the potential equals 0. So the net potential at that point B is equal to 0. All right. In the concept test, we had several questions sort of related to that. You can go back and look at those as well. We might see some other problems that are similar to this. So that's one other problem that you'll definitely have tomorrow. I mean, not tomorrow. When? I don't know. Monday, right. Okay. This problem right here is to deal with equipotential lines. Remember, equipotential lines always run perpendicular to the electric field. So my equipotential line here moves in this direction. And along an equipotential line, no work is required to move a charge. Because equipotential means along that line you have the same potential energy. Equipotential means the same potential energy. And so if your energy of your charge doesn't change, then that means that that you don't require any work to move it, because you're not changing its energy. All right, so no work is required to move that charge. So in this question, for example, how much work is done to move the particle? It would be A, 0 work, because I'm moving along an equipotential line. Also, if I'm moving in different directions, so for example, if I'm moving along the field lines, that requires negative work. And if I'm moving opposed to the field lines, that requires positive work. You can think about this. These are all for positive charge, by the way. So if I have a positive charge, a plus Q, think about it in this way. If I have a positive charge, the electric field is trying to move that charge in that direction. So I have to apply a force in this direction to make it move in that direction. So I have a force and a displacement in that direction. That's positive work. However, here, if I have a positive charge, the field is trying to move it in that direction. So the field is already moving in that direction. If I actually have to pull back and sort of slow it down. If you want to think about it in that way, that's sort of true. So if I'm pulling back in this direction, and yet it's still moving in that direction, that's opposite force and displacement, that's negative work. And then here, if I'm moving along in this direction, that's no work at all. All right, because I have to move it in this direction, positive charge, I have to apply a force in this direction, and the displacement's in that direction, so that's no work, because my force and displacement are not in the same direction. You can see a problem like that, interpreting the amount of work required to move a charge in an electric field. All right, you need to know your conservative forces and charges. Conservative forces, rather. Only field forces are conservative. Electric force and gravitational forces are conservative. Remember, potential is a measure of, or if we think about our three big ideas, forces, electric fields are forces per charge, and potential is what per what? Big idea. If potential is a measure of what per what? Remember? That's right, Corinne. Yeah, it's energy per charge. Potential is energy per charge. All right, so you need to remember that's sort of a big idea. It's on your equation sheet. It says like V, something along these lines is PE over Q. Or I think it might say actually PE is Q times V or something like that. But potential is energy per charge. All right. This problem right here is similar to one we've seen. You can see something like this. If I want to know the potential in the electric field at the point in the middle, the potential is easy. I just add up the number of positive and negative charges. If they're the same, then the potential is 0. If I have more positive than negative charges, the potential is positive. If I have more negative than positive, the potential is negative. All right. The field is a little more complicated. You have to imagine a positive point source. This is how we determine the direction of an electric field. We put a positive point charge at that point P, and then we ask ourselves, what is the direction of the electric force? And then that is the direction of the electric field. So for example, at that point P, due to this charge, my electric field is in that direction because it's a positive charge. Due to this charge, it's in this direction because it's a negative charge and they're being attracted to one another. That is my imaginary positive test charge there and this negative particle. Due to this charge, it's in this direction, and then due to this charge, it's in this direction. So the electric field there is not 0. So B would be the right answer. Okay, let's look at this one right here. Again, this is talking about kinetic energy, but this idea still holds. In fact, we can think more generally that our potential V is equal to energy per charge. So if I have a charge that goes across a potential difference, in this case, the potential difference is going from 5 to -5. So I have a net potential difference going from 5 to -5. Think about the number line, right? I'm going from 5 to 4 to 3 to 2 to 1 to 0, and then back to -5. So my net potential difference is what? What? Not 5, but 10. So I'm going from 5 to -5. So my potential difference between those two plates is 10 volts. So if I want to know how much kinetic energy does the charge have moving across these two plates, I just say energy is equal to the potential times the charge. That's 10 volts times 2 coulombs, which is 20 joules. So A would be the right answer. All right. Am I moving too fast, y'all? But we've seen all this before, so hopefully we just sort of want to cover everything that we can. 23? Yeah. All right, so you will have to interpret field lines, and this is a good question where you have to interpret field lines. There are a couple of things that you do. Actually, 23 and 24 were similar. The first one just asks, what's the sign of the charge? Here I have field lines coming out of the charge. Whenever I have fields coming out of the charge, that's a positive charge. Field lines come out of positive charges, they go into negative charges. They come out of positive, go into negative. All right, so you will have a question like we had, I think on the concept test, where you have, I give you a couple of charges and I show you the field lines, and I give you the magnitude of one of the charges and ask you what is the charge of the other. All right, y'all remember what I'm talking about? I had that on the concept test. We'll see one later, I'm sure. So here, the answer is that Q is positive because the field lines are coming out. And then it also asks, where is the electric potential the least? For this number 24, is it A, B, C, or D, or some combination, C and B, or A and B? So where is it the least? Remember, our potential is KQ over R. So does R be big or small for B to be small? It should be big. As R goes up, your potential goes down. As I move a charge away from this charge, its potential for motion goes down. Because if the force decreases, it has less potential energy. So as I move a charge away, because R goes up, B goes down. Inverse relationship. So I'm looking for the least potential energy. A is far out, B is far out too. So the answer was E, both A and B. The highest potential is at close in, point B, it looks like. All right, number 27 here. You want to remember this idea that do negative charges move high to low or low to high, and positive charges move low to high. You know, I don't even remember. This is the way I always remember, is I'll draw two charge plates. This is positive, this is negative. I know that the positive is the high and the negative is the low. And then I imagine, okay, well, if I put a positive charge here, it's going to move in this direction. So positive charges move from high to low. So for example, if I left, well, and then negative charges, if I put a negative charge, it's going to move in that direction. So negative charges move from low to high. Since I know this, I'm just thinking about, all right, well, this positive charge is repelled from the positive plate and attracted to the negative plate. If that helps you to think about it, it helps me to think about it. If it helps you, that's great. If not, that's fine too. Just remember those rules. Positive charges move from high to low potential. Negative charges move from low to high potential. All right. So here, if I have an electron, it's at point A. Electrons move from low to high. So an electron is going to move in that direction, because in that direction, the potential actually increases. I'm moving from a low potential to a higher potential. We like to do this thing at my house. Y'all can do this. You can try it out. You know, like low and high, like the pitch. I always try to get my kids to do this. They find it very difficult. How's it go? Low, high, low, high. It's not very easy to do that. Can y'all do it? Try it right quick. Very good. It's not easy. All right. Okay. We're not here to mess around there. Can I clear this? I'm very serious. Okay. What amount of work is required to assemble this collection of charges? You know, if you look back at the old tests, the solutions for this were different. But the way I showed y'all, let me show you a different way to do this. Some of them I might have done it this way, but our potential energy of our charges is KQQ over R. Isn't that right? It's R, right? Not R squared. Yeah, KQQ, oh yeah, KQQ over R. Huh? Right, and I can think about this collection of charges as three separate pairs of charges. And then when I calculate the potential energy, I calculate the potential energy of one of those pairs, a second of those pairs, and a third of those pairs. And then the total potential energy is just the sum of those three numbers. All right? And then the work required is equal to the potential energy. So, for example, if I take the potential energy of these two charges, that's 9 times 10 to the 9th. 3 times 10 to the minus 9, 2 times 10 to the minus 9, divided by this distance. Listen, guys, you got to know the 3, 4, 5 triangle, because it'll save you a lot of headache. Because you will. That's my triangle of choice for tomorrow, okay, or for Friday or whatever. Divided by 5 meters, because I don't want y'all messing around with inverse tans and Pythagorean business. So just remember that triangle 3, 4, 5. It will help you to remember the angles too. This is 37 degrees. That's the side opposite the little side, and this is 53 degrees. But if you can't remember those, just remember the 3, 4, 5. Remember again, it'll help you to be able to cancel some of this business out, and so we're left with 54 over 5 times 10 to the minus 9 joules. Then you would do the same. I'm not going to do it here, but you would do the same for this pair. Figure out what is the potential energy, and then the same for this pair. Figure out what is the potential energy, and then add all three of those numbers up. Okay? Now, it's not here, but let me just warn you that whenever you're dealing with these scalar quantities, like potential and potential energy, you always include the signs of the charges. Okay. When we deal with vector quantities, we're including the signs, but we're not writing them when we do the calculations because the signs are inherent when we draw the vectors. Like we assume the signs when we draw the direction of the vector. But anytime we deal with scalar quantities, and we deal with scalar quantities with potential and potential energy, those are only two scalar quantities, you're going to use the sign of the charges. So for example, if this was negative 3 nanocoulombs, I would write a negative 3 nanocoulombs here. And then this value would come out negative. And then when you add up the numbers, you would add up in a negative number. So it would be a difference and not a sum. Okay? That's important. I got that? Because you will see some negative charges. I'm pretty sure that you had to take it into account. But of course, like all the other questions, like I'll go through and make the common mistakes. And so just because you get an answer doesn't mean it's right. It could be that you made a common mistake and you're getting an answer that's there, but it's not the correct answer. Okay? Just be aware. So don't be too confident if you got an answer. Oh, I can look and see. Can I clear this? I don't want to see number 28 is C. Yeah, 24 nanojoules. All right. I'll take this away. All right, let's look at some field stuff too. Those potential. That's probably the hardest part. Like I find potential very difficult. Okay, here's a basic kinematics problem. So I have a proton that's 3 meters from a 1 nanocoulomb charge. What initial acceleration does it experience? Well, first we need to recognize that F is equal to Q times E. So this proton has a force on it due to this 1 nanocoulomb charge. We don't care about the direction of it, it's just asking for the magnitude, so don't worry about if it's attractive or repulsive. Q is, wait, no, I'm sorry. I don't have the electric field, this is different. My force here is from Coulomb's law. So it's going to be KQQ over R squared. That's going to be 9 times 10 to the 9th. Q of a proton is 1.6 times 10 to the minus, 19? And our 1 nanocoulomb charge is 1 times 10 to the minus 9 divided by 3 meters squared. So this cancels with this cancels with this. And I'm left with a force of 1.6 times 10 to the minus 19. All right. And then if I want to know the acceleration, that's just F over m divided by the mass of a proton. Let's see, it's the bigger, so it's 1.67 times 10 to the minus 27. All right. And then, before I even look at my calculator, I can say, well, these two basically cancel out. They're both 1.6 basically. So that's 10 to the minus 19 over 10 to the minus 27, which is 10 to the 8th. All right. If I take this 10 to the minus 27 up to the numerator, it becomes positive. So it's 10 to the minus 19 times 10 to the positive 27, which is 10 to the 8th, which is B. It's 10 to the 8th, right? Yeah, there are 8 zeros. So B is the answer. Alrighty. Basic kinematics. I could also ask you, in so many seconds, say, I don't know, in 2 seconds, what is the velocity? Well, velocity is equal to V0 plus AT. V0 would be 0, unless it said otherwise. Yeah, Whitney?
Could you work it out using the other formula, the F equals QE?
Yeah. Yeah, you'd have to calculate the electric field. Oh, you want to do that? It's worthwhile to do. Let's go ahead and do it. So let's say, let me finish this right quick, and then I'll come back to that. So our velocity then would be the acceleration, which is, 10 to the 8th times 2 seconds, or 2 times 10 to the 8th meters per second. I could also ask you the distance. All right, remember x is 1/2 AT squared, assuming that our initial velocity would be 0, which it will be. So just one kinematics problem. But a lot about forces. You could approach this a different way. So you could ask, well, first, what is the electric field 3 meters from this 1 nanocoulomb charge? You will have a problem where you have to calculate the electric field due to one or more charges, or one charge and actually more than one charge, either in one dimension or in two dimensions. Actually, both in one dimension and in two dimensions. I'll show you that. So, to calculate that electric field is kq over r squared, 9 times 10 to the 9th. Q is our 1 nanocoulomb charge, 1 times 10 to the minus 9, divided by 3 meters squared. This is real easy because the 3 squared cancels out with the 9. This cancels. And so I'm left with an electric field of 1 Newton per Coulomb. And then if I want to know the force, it's just Q times E. So that's 1.6 times 10 to the minus 19. I'm looking for the force on the proton. So that's why I use this charge here times 1 Newton per Coulomb. And then that gives me the force that I found right here. Because you see, I mean, our electric field times Q is just Coulomb's law. The electric field is based on Coulomb's law. KQ over R squared times Q is the force. Is that clear? Let's do some more electric field stuff because, yeah, Jada. Oh, the M right here. It's on your equation sheet. This is the mass of the proton. You won't see too many questions where you have to do an electron or a proton, but I think there's one or two. But just be aware that the masses are on the equation sheet. And it's not going to say charge of electron, charge of proton. It's just going to say 1e, right? It's 1.6 times 10 to the minus 19. That's the fundamental unit of charge, and that is on your equation sheet. It's on the website, so I recommend it. If you're not real familiar with it, print it out and just make sure you know what's on there. Because there's a lot of information on there. You're only really involved with one little section. Hey, my wife got me these pens.
Do you love them?
I love them. Look at this. I'm sorry. Yeah.
No, absolutely.
You got them too? Like I've always used these flare pens, but at Office Depot they have the multi-cut. She got it. It's not expensive, like $15. So she bought it for me and the kids, and we had to split them up. So we like took turns picking our favorite color. But then I went out and bought my own. I can brought it up here to work. All right. Don't forget your units. So make sure you know your units, especially of the electric field. You know, we had 2 sets of units for the electric field. Let's just write those down right here. We had electric field is 1 Newton per Coulomb, or rather 1 Newton per Coulomb is equivalent to 1 volt per meter. That came up a little bit later when we started talking about potential and electric fields and how they're related. The equation that relates electric fields and potential is on your equation sheet. But it's just useful to know that these are the units, because sometimes we see them. And then also, you know, the basic SI units for electric field are, well, a Newton is a kilogram meter per second squared divided by Coulomb. So those are all equivalent. 1 Newton per Coulomb is equivalent to 1 volt per meter, is equivalent to 1 kilogram meter per Coulomb second squared. I just said kilogram meter per second squared, that's a Newton, and then 1 over Coulomb. These are the basic SI units of the electric field. You need to be able to do that anyway. I can just sort of kick in questions like that with basic SI units. And you just look at the equation and plug in the right units for each variable. Okay? All right. Can I clear this? Okay, you'll have a question like this where I give you a collection of charges and ask you what the forces are. Okay with that? Yeah. Okay, let's, yeah, number 4. All right, so here I have I do that. Don't I?
You said a little inductor was negatives and it made the L positive or something?
That's not what it says right there, is it? Yeah, I'm sorry. So here I have a positive charge right here. This is positive. And yeah, so it will set up an induced charge of negative and positive, like while they're touching. And then what do? You pull them apart. Oh yeah, and then you pull them apart. And so as a result, L would be negative and M would be positive. Did I not say that on the thing?
I think you corrected yourself, but you just kind of...
I'm sorry, the words just got all garbled up. Okay?
So the positive charge
does that because the charge has to flow through.
Right, they're touching because when you bring the thing up here like this, right, they have to, it sets up this induced charge where all the negative charges come over here and you're left with positive charges over here. Remember too, when we talk about the movement of charges, we're talking about electrons that are moving around. So you never really move protons, you're always moving electrons. Okay? So when I talk about this, it's always the electrons that are going away to some other place, not the protons. Let's imagine three charges. I don't have a problem right out of hand, but let me just sort of set it up for you. Let's imagine that I have three charges on a line. I know two of the charges. Let's say this is -1 coulomb, this is 2 coulombs, and this is a charge Q. Could you tell me what Q is? Let's say this is, I don't know, 1 meter. This is 2 meters. Could you find Q such that the force on the 2 coulomb charge is 0, for example? Let me show you how to set it up. So let me write that. I think there's a question similar to this somewhere, but I'm not sure where it is. So what is Q so that F for the 2 coulomb charge equals 0? All right, so what you do here, and guys, you could see some 1D yet multi-charge problems like this. What I do here is I draw the force vectors, so I know due to this charge, my force has to be in this direction. So therefore, the force due to this charge has to be in this direction. So first of all, I know that Q has to be negative in charge. All right, so then I could go through my solutions and say, well, this was positive, I get rid of all those. And that's just generally good practice, that you go through your possible answers and get rid of those that aren't relevant, or certainly aren't the answer. And then I would just set the magnitudes of these two forces equal to one another. So for example, the one in red is going to be K times 2 coulombs times -1 coulomb divided by 1 meter squared, and then that would equal to the magnitude of this charge, which would be, excuse me, this should be a +1. Remember, when we're doing these vector things, we don't put in the signs. And then the other force would be K 2 coulombs Q divided by 1 meter squared. And so of course here Q would be what? This was really simple. Because they're the same distance apart, everything cancels out except for Q would then be equal to 1 coulomb. But you could have simple problems too. But you could also make it a little more complicated by having these distances. Oh, these distances were different. I'm sorry. So that's not the case then. So here, this would be 2 meters squared. And then you'd have to go through and solve for what is Q. Y'all clear on what I mean by that? Well, because in order for the force on this charge to be 0, it has to have equal and opposite forces. Right? So that's the condition, that the net force is equal to 0. All right. You might see a few questions that you've seen before in the Old Testament. For the most part, they're all new questions. But the Old Testament helped you, okay? Yeah, I do take a few questions from the Old Testament, not just a few, really. Homework at home. concept test, I think questions from there. Questions? Particular questions? Oh my god, 20 minutes is gone. Can I take this away? Want to look at some old tests? We'll just peruse through some of the old tests. I think I've hit all the high spots. But Andrew, you asked a question? Conceptual type things? Yeah, let's look at some of the other questions. I mean, some of the other tests. Is that okay? And we'll see what we have on there. Can I tell you something first? So this, you want to hear it? Like, I'm reading this book for this class that I'm taking, and I'm reading this chapter on language, and they have a section on humor, and they tell about this guy that did this study to determine the funniest joke ever. And so he put it this website, it had like 40,000 jokes, and millions of people came in and they voted on what the funniest joke was. You want to hear what the funniest joke was? This week, you want to hear it? It's a long joke. I don't usually tell these, but it's a long one. It's not real long. But there were two guys, and they were out hunting. And then something happened to one of the guys. You know, like he fell down, and he was cold, and he thought he was dead. And so the other guy called 911 and said to the operator, hey, we're out in the woods. My friend, I think he died. And the 911 operator, okay, sir, just calm down. Everything's going to be okay. But first, just go over and just want to make sure that he's actually dead. And then so the guy goes, and he says, okay, just a second. So he goes over to the guy, and the lady on the operator, she hears a gunshot in the background. And then the guy comes back, and he says, okay, now what do I do? That was a little bit funny. All right. So let's. You need to know about electrical insulators versus conductors. Remember, conductors, electrons move freely in conductors. Insulators, they don't move freely. All right, conductors, metals. Insulators are plastics, rubbers, wood, air. Dimensions. You need to know the dimensions of our electric field. We talked about this, but let me show you. So here, you will have a question like this. It won't be this configuration of charges, but here I give you this electric field, and I tell you that the charge on the right has a magnitude of 10 microcoulombs. I know that it has to be plus 10 because the field lines are coming out. Field lines only come out of positive charges. So this one has to be a negative something. I can get rid of these two. And then I go and I count the number of lines. I see 1, 2, 3, 4, 5, 6, 7, 8, 3, 4, 5, 6, 7, 8, 9, 10 lines over here, and 4 lines over there. That means that this is, if this is 10 microcoulombs, this one is 4/10 of 10. No, that's not right. Yeah, that's right. 4/10 of 10 or minus 4. You'll follow me? You set up a ratio. That one's not real easy. It's not an even ratio. Okay? Problem like this, sort of talked about that already. So you already did one like this. This is the kinematics, no capacitors. So we're done there. Goodness, we were zooming, that's nice too. All right. You'll have a question like this where you have 3 charges on a line, either electric field, or where you're dealing with the force or the field of 2 charges in a straight line. You'll have one like this. This one is just finding the direction. See, we already talked about all this. If you see something, yell out, okay? But, and this one, it was just asking the charge with a larger magnitude. The way you would tell this is by looking at the equipotential lines. Over here I have an equipotential line of almost 70 volts, whereas about the same distance over here I have minus 20 volts. So that means this is the bigger magnitude charge because the voltage is bigger. Let's see, we already talked about one of these. And then capacitors to take this away. Can't tell.
For number 6, I kind of had a hard time differentiating between two answers, B and D. The negative charges in her hair and the excess negative charges in her hair.
Oh yeah. So the answer is D, because the negative charges don't all move to the ends of her hair, right? She actually had negative charges all along the strands of the hair. You understand the difference?
I know that the hair's, I don't know.
The hair sort of.
It was kind of like a 50-50 question for me. Like,
I
think it's either
understand.
B or D. I didn't
Yeah.
know how to.
No, I agree. It's not very comforting that way. But the correct answer, B, is not really correct because the charges don't move all to the tips of the hair. They're all along the hair.
Okay.
All right. Oh, okay, here's a good one. So this charge is sitting in an electric field and it moves in that direction to the left. What is the sign? Remember, positive charges feel a force in the same direction as the electric field. So negative charges feel a force that's in the opposite direction of the field. So what is the sign of this charge? It's negative, right? Because it's feeling a force opposite the electric field. Fields and forces are closely related. And that's it for that one. I'm running out of material here. So if y'all have any particular questions, but I'll sort of go through these, make sure I haven't missed any big topics. Kinematics, so we talked about that already. Already did one like this. Net force on a charge. We've done one like this. I showed you one earlier, but one similar to this. You just want to find draw the force vectors due to the two charges on either side. Or actually, in this case, the force vectors would look like that. It'd be attracted to this charge and repelled from this charge. Find the magnitudes of them with Coulomb's law, and then add those up. Which of these is not a valid charge? You just take each number and divide by the fundamental unit of charge, 1.6 times 10 to the 19. And whichever one is a decimal is not the right answer, because you can't have a fraction of an electron or proton. Let's talk about that. Okay, this one's good. You can see something like this. Where is the electric field the greatest in magnitude? I think we worked on like this in class actually. Where I can just draw the electric field vectors. So for example here, due to this charge, electric field vector in that direction. Due to this charge, it's going to be in that direction. Excuse me. Over here, due to the minus 4q, I get it in that direction. And then due to this charge, because I'm a lot farther away and it's a smaller charge, I get an electric field vector in that direction. So some questions just sort of asking you about interpreting electric field vectors like that. How much work for this one to move along the electric field like that? 0 work, very good. Some basic things about charges. We had some concept test questions. You could see something like this. Similarly here, these two charges, an electron and a proton, are moving across a potential difference. Which particle has more kinetic energy? Remember, potential is energy per charge. The potential difference is the same for both. The charge is the same for both, so the energy is the same for both. This is straight out of concept test. Here's a potential of multiple charges. We've already done one like this, but finding the potential due to these two charges at this point. So you see, there are a lot of similar problems, and you'll see the same. They'll just be different numbers, different scenarios, and what have you. Direction of the electric field. In this case, would the electric field be to the left or the right? If the electron is moving to the right, feels a force to the right, what's right? The electric field is the opposite direction because it's a negative particle. So we've already done one similar to these. This is the amount of work done. This is where you take those collections of pairs. So I consider the potential energy of this pair, and this pair. And then add those up. Potential is greatest at C and D when you're close. And then capacitors. Alright, I think that's about it. Unless y'all have particular questions. I think that's about all that I have.
When you said C and D was close, like potential was greatest, that's just because of the distance is smaller.
Right, yeah, the distances were smaller, and since V is KQ over R, as R goes down, V goes up. It's an inverse relationship. Or you can think about it, as you get closer to the charge, the force gets bigger, and so you have more potential for motion.
Sort of like we skip that section where it's talking about the different charges if you know the potential between.
Different charges.
If you had a plus and a minus, comparing like, I guess that a plus and a minus would have more potential if it's farther away.
I don't remember what you're talking about. Can you show me?
I thought like it was, like if you had a plus and minus charge, you think further away, it would have greater potential because they're more likely.
Oh yeah, we sort of skipped the whole semantics of getting around to voltage, like how voltage is defined. It's really just sort of an argument leading up to the sign. Yeah, it's not really that important. I mean, it is important for sort of underlying ideas, but for the mechanics of it, it's not that important.
Like some of that concept test ones, like electric potential.
Mm-hmm.
Can you do some of those?
Yeah. Let's see. So, like from the concept test. Well, I haven't uploaded those concept tests yet, have I? I don't think they're up there. No. I'll upload those. I think, yeah, the final quiz is tonight, so I'll upload it in the morning. The concept test for potential. Yeah, so I think it's a good practice to just print these out and then go through them. I print them, I mean, I don't print them because I'm not taking the test, but you can print them 6 slides to a page, and then you can fold the page in half, and you can have the question on one side and the answer on the other side. All right, so let's see, this one, we've done similar one here. Well, no, let's just say feel the same magnitude force because they're in an electric field in the opposite direction. What in particular here, Andrew? 2.3? Like this one?
Yeah, I didn't have a mistake between.
Okay. Well, if I want to know the electric potential at point A, yeah, this is different from what we skipped. Like that was a whole different, that was just sort of a line of reasoning. This is not what we skipped. Okay, so if I have a positive charge here and a negative charge here, at this point, I have potentials due to both of them. Because I'm closer to the positive charge, the positive potential is bigger than the negative potential. All right, so the potential due to this charge is bigger at this point than the potential due to this negative charge. So the net potential over here is positive at point A, because I'm closer to the positive charge. Right? And then it asks a similar question, like what is the potential at point B? At point B, I'm equidistant from these two charges, and so they're equal. The potential due to the positive and the negative charge is equal, so my potential is equal to 0.
I couldn't see the positive and negative, it's so small.
Yeah, it is kind of small.
Sorry, I didn't know what was going on.
Yeah. Sorry. What else? We've been through a lot of these in the old test. Yeah, I think Yeah, a lot of these are familiar, right? Like we've seen a lot of these, so yeah, and that's it. All right, we can talk if you want, Andrew. I'm gonna cut it. I'm gonna close the session though. If y'all want to hang around though, you're welcome to. And if you, well, we can talk about some more. I don't want to cut you off, but